Okay, there was an issue with the with the camcorder memory card, so I'm just gonna complete the rest of this presentation so that it's all on uh, the video. Um, okay, so we've sort of talked about what's the situation at 0 Kelvin, but if you have a finite temperature, then how are the sorry, let me get a laser pointer. Okay, how are the electronic states occupied? And like I mentioned, electrons are fermions, so you can only have one electron um, per spin orbital. And so you cannot use a Boltzmann function to describe the population of states. And you have to use a Fermi-Dirac statistics. So you have to use a Fermi distribution. And the Fermi distribution essentially guarantees that the Pauli principle is observed. And this is the form of the Fermi distribution. It's 1 over an exponential plus 1. And this exponential involves the energy of the state minus the chemical potential over kT. At T equals 0, the chemical potential would be exactly equal to the Fermi energy. At higher temperatures, it can deviate a bit from that. But you can think of this mu as being approximately equal to the Fermi energy. And basically the, the energetic region for which the Fermi function deviates significantly from a step function is on the order of 2 kT. And so here's what the Fermi function looks like if you plot it at T equals 0. It looks like a step function, right? So all of the electronic states are occupied up to the Fermi energy, and then they stop being occupied. But at finite temperature, you start to sort of round off the edges of this step function, and you start to have a significant portion of the distribution with an energy greater than the Fermi energy that are occupied, and you start to have unoccupied states that are below the Fermi energy. And so these are called hole states. And so the energetic difference between the occupied excited electronic states and the hole states has a characteristic energy of about 2 kT, right? And so as you increase the temperature, you start to have holes at lower and lower energies and excited electrons at higher and higher energies. Okay, so if you want to know the total number of electrons at each energy, you need to multiply this occupation function, f of E and T, times the density of states at a particular energy. And if you do that, so this curve is sort of turned over on its side. So energy is on the y-axis, density of states, or I'm sorry, the probability times the density, right? So the total electron occupation at each energy is on the x-axis. And you have this density of states times the Fermi function. And so the density of states looks like the square root of energy. It grows as the square root of energy, so it looks like this. And so then this function gets multiplied by this thing that looks like a sort of rounded off step function. And if you multiply these two functions together, then you get a distribution that looks kind of like this curve here. Okay. So I mentioned that this model was very, very successful for gold. For some other metals, it's a little bit less successful. In particular, when you have contributions of the d orbital electrons to the conduction band, then the picture can look a little bit differently. So it can look a little different. So if you look at nickel, for example, if you look at the density of states as a function of energy, at low energy, the picture resembles the model that we derive, right? So the density of states grows as the square root of the energy. But as you go to higher energy, you start to see this extra structure. This is due to the structure of the d orbitals that are involved in the conduction band of nickel, right? So in gold, we only had the s band contributing to the conduction band, but if you have also d electrons, then you get a more complicated structure. But you still qualitatively have the same effect, which is that you fill all of the states up until a certain energy where you run out of electrons, and this is the Fermi energy. And then, if you have a 0 Kelvin metal, all the states above that energy are going to be unoccupied. Okay. All right. So the next topic that we want to talk about is dynamics at surfaces and how the electronic states, particularly at metal surfaces, can play a role in the dynamics. And so as an example, we'll look at the scattering of hydrogen atoms from metal surfaces. And this will let us look at translational to electronic energy coupling. So coupling of energy between the translation of a hydrogen atom and the electronic degrees of freedom of the surface. And this is very important for chemistry because we know that hydrogen atoms stick at metal surfaces with a very high probability. But why is that the case? Because if you consider simple, you know, classical mechanics, right? Then if you have the collision, if you consider a hard sphere collision between a mass, right, a particle of mass 1 and a particle of mass 2, let's say initially the particle of mass 1 has velocity v1, the particle of mass 2 is initially at rest, and then they undergo a hard sphere collision. And after the collision, particle 1 has speed v1 prime, particle 2 has speed v2 prime. If you just consider an elastic collision that conserves momentum and that conserves kinetic energy, then you can take these two equations and solve for the two unknowns, v1 prime and v2 prime. And if you take the ratio then of v1 prime to v1 initial, right? So v1 prime squared over v1 squared, then this is the expression that you get. And so basically the amount of momentum that can be transferred depends on the masses of the two particles. And so if mass 1 and mass 2 are the same, then after the collision, v1 prime is going to be 0, right? m1 minus m2 would be 0 in that case. And so that's kind of like the familiar case of if you're playing billiards, and if you shoot one of the billiard balls directly at another one so that it strikes it directly in the center, then essentially you're able to transfer all of the momentum from the one billiard ball to the other. But if there's a large mass mismatch, right? So if mass 1 is much less than mass 2, then this ratio is going to be very similar to 1, right? Because both the numerator and the denominator are going to be similar to m2 squared. And so that would be the case, like if you take a ping pong ball, mass 1, and throw it at a bowling ball, mass 2, right? Then the ping pong ball is just going to scatter off the bowling ball, and you're barely going to transfer any momentum at all. And so would be the case if you have a hydrogen atom colliding with a gold molecule, because hydrogen atoms are very light relative to gold. And so if you look at v1 prime squared over v1 squared as a function of m1 over m2, then for very small m1, you expect this ratio to be very close to 1. So in other words, all of the velocity is retained in the light atom, right? And then the ratio decreases as the mass ratio approaches 1. And so for hydrogen atoms on gold, the mass of hydrogen is 1, the mass of a gold atom is 197 atomic mass units. And so you would expect the ratio of v1 squared after the collision to be 0.98. So in other words, you're only going to transfer about 2% of the incidence kinetic energy to the gold atom, assuming that the collision happens between one hydrogen atom and one gold atom. Right? So if hydrogen atoms can only dissipate 2% of their energy when they strike a gold surface, how are they ever going to be able to stick to the surface, right? They're never going to be able to dissipate enough energy in order to stick. And so the answer is that there are other mechanisms for energy dissipation. So these can be investigated experimentally by doing a scattering experiment. So you can take a beam of hydrogen atoms at a very well controlled incident kinetic energy, scatter it from a gold surface, and you can investigate the detailed dynamics of this scattering process by looking at the scattered hydrogen atoms. You can measure the angular distributions, and you can also measure the final kinetic energy distribution. And if you then look at the incidence kinetic energy minus the final kinetic energy of the scattered atoms, then this difference has to be the amount of energy that was transferred to the surface. And we can look here at the results of an experiment like this. So in this experiment, there's an incident beam of hydrogen atoms with an incidence energy of 2.7 electron volts. So on the scale of this graph, the incidence energy is here. There's two experiments that are being compared. So first, we can look at this experiment whose results are shown in blue. In this experiment, you take a gold surface and you cover it with a whole bunch of xenon atoms. So you have overlayers of xenon atoms on the gold surface. And then you scatter a hydrogen atom from the xenon atoms. And you look at the kinetic energy loss in the hydrogen atom, right? So the final minus initial energy, kinetic energy of the hydrogen atoms. And you see that there's only a very small amount of kinetic energy loss in the hydrogen atoms. So this black distribution would be what you would expect if there were no kinetic energy loss. This basically gives you the width of the energy profile of the incident beam of hydrogen atoms. And this blue distribution here is the energy loss after scattering from the xenon atoms. So there's a very small kinetic energy loss that's consistent with the Pauli limit for basically a hard sphere collision with the xenon atom. On the other hand, if you remove the xenon atoms from the surface so that you just have a bare gold surface, then you scatter hydrogen atoms from the gold surface and you end up with this kinetic energy loss distribution that's shown in red. So you lose a lot of kinetic energy from the hydrogen atom during this process, and you get a broad distribution of kinetic energy losses. And this situation is clearly very, very different than the situation that happens when you scatter hydrogen from xenon, even though xenon and gold have a similar mass. So that tells you that the mechanism for the energy loss has to be different for the metal atoms, right? For the atoms of the metal surface. And so, in fact, what's taking place is the hydrogen atoms are able to couple to the electronic degrees of freedom of the metal surface. And as the hydrogen atom collides with the metal surface, it's able, via non-adiabatic dynamics, it's able to transfer part of its kinetic energy to the surface by exciting electrons from the surface into excited electronic states. And there can be many, many of these electronic excitations taking place as the hydrogen atom is basically interacting with the electrons of the metal. And qualitatively, this is described using a theory called electronic friction theory, where basically as the hydrogen atom is colliding with the surface, it experiences a friction-like force due to these electrons of the surface that basically are getting excited to higher states and taking away energy from the hydrogen atom. Okay, and also, of course, this has very important implications for chemistry because a lot of important hydrogen atom chemistry takes place at metal surfaces. So a lot of transition metals are used as hydrogenation catalysts. But if hydrogen atoms were not able to stick to the metal surfaces, then a lot of this chemistry wouldn't take place. And so, this ability of hydrogen to dissipate its energy to the electronic degrees of freedom of the surface, of course, has important implications for hydrogenation chemistry at metal surfaces. Okay, so next, we'll consider one other type of energy transfer, and that is energy transfer between the electronic degrees of freedom of the surface to vibrational degrees of freedom of molecules. And so the example that we'll consider is diatomic molecules, NO, scattering again from the gold 111 surface. So we're going to have an incident beam of NO molecules scattering from a gold 111 surface, and we're going to look at the vibrationally excited molecules that arise as scattering products. And we're going to look at an experiment that is probing direct scatter. So in other words, just single collision scattering of NO from the surface. Okay, and so so here's the process. We're going to take a incident beam of NO. initially in V=0 state, scatter it from a gold surface, and then we're going to look for vibrational excitation in the scattering products. And we're going to look for the vibrational distribution using resonance-enhanced multiphoton ionization spectroscopy, right? And so since this is a resonant technique, like we discussed this technique several lectures ago, you can use it to probe the population of molecules in different internal states. So shown here are REMPI spectra probing the V=1 state and the V=2 states. And right, so these occur at different photon energies, right? You can see these different states, right, by tuning your laser to a different energy. The structure here is due to different rotational states within each vibrational level. And so in order to get the total population in the V=1 state and the V=2 state, you integrate over the all of the rotations, right? You can also get the total population in V=0 by looking at a different frequency that's not shown. But one thing to note is that there's a very strong dependence here on the temperature of the surface. So if you go from 500 degrees Celsius to 700 degrees Celsius surface temperature, you see significantly more vibrational excitation, especially in V=2. Okay, yeah, I should mention before we move on, naively you might expect, okay, so you increase the temperature and the vibrational population increases. That's an indication that the vibrational energy has to be coming from the surface degrees of freedom. It's not coming from the incidence kinetic energy being converted to vibration, right? But it must be coming from degrees of freedom that are excited when you excite the surface to a higher temperature. But there are sort of two effects that you can consider. You could consider the phonons of the surface transferring energy to the molecules, or you could consider excited electron-hole pairs transferring their energy to the molecules. But like we talked about last time, the structure of the phonons is very different than the structure of the electronic degrees of freedom. And the phonon vibrations have a very hard cutoff frequency at the Debye frequency. And the Debye frequency for gold is only about 200 reciprocal centimeters, whereas the vibrational frequency of NO is about 2000 reciprocal centimeters. So in order for the phonons to excite the NO stretch, you would have to have a 10 phonon process. So you would have to have a NO molecule scattering in a sub-picosecond direct scatter mechanism from the surface and somehow absorbing 10 phonons worth of energy from the surface, in a concerted process. And the probability of that happening is basically zero. So what has to be going on is that the electronic degrees of freedom of the surface are being used to excite the vibration of the molecule. And there's in fact a pseudo-Arrhenius dependence on the temperature of the surface. So if you look at the probability of exciting a particular vibrational state, right, on a logarithmic scale, as a function of 1 over the surface temperature, then you see basically these linear curves. The blue curve is for the probability of exciting V=1, and the red curve here is for the probability of exciting V=2. You can see the probability of exciting V=1 is significantly higher, but you can also see that the effective activation energy that's derived from this Arrhenius type plot is different for the two vibrational states. And so if you look at the slope of the plot, for V=1, you get an effective activation energy of about 2000 reciprocal centimeters. For V=2, you get an activation energy that's about 2 times as high. And in fact, the activation energy that's derived from experiment is very close to the vibrational level spacing between V=0 and V=1, and between V=0 and V=2. Okay, so why do you get this pseudo-Arrhenius behavior? Well, basically, the reason for that is that there has to be an electron-hole pair that has enough energy to be able to excite the vibrational motion of the molecule. And so if you had the surface at t equals 0, then there would be no excited electron hole pairs, right? The occupation probability of the electronic states would just be a step function. Um, However, as you increase the temperature, you start to have a tail of the distribution that corresponds to excited electrons, and you start to have a portion of the distribution that has vacancies, right, which we call holes. And so if you have an electron that's interacting with the molecule and it's transferring its electronic energy to the vibration of the molecule, right, then at a certain temperature, you start to have electron hole pairs with an energetic difference that is great enough to excite a quantum of vibration in the molecule. And of course, to excite two quanta of vibration, you would need more energy. And so you can come up with a simple theory describing the probability of finding an electron hole pair whose energy gap matches the vibrational transition. And this probability could be found by integrating over the energy of each electron times an integral over the, or nested with an integral over the energy of each hole, right, which I'll call E prime. Then you take the probability of a state at each electron energy times the probability of having a vacant site at each energy. And then you multiply by a delta function that requires the difference in energy between E and E prime to match the vibrational energy. And if you do this, what ends up being the result is you get a function probability of vibrational excitation. And then this has the form of an Arrhenius equation. So it has a prefactor times a exponential of a certain energy over kT, where this energy, this effective activation energy, ends up being exactly equal to the vibrational energy that is excited in the molecule. And this is exactly the form that is observed in the experiment, right? We see these Arrhenius curves where the activation energy matches the vibrational energy that is excited in the molecule. Okay, so that is basically all the topics that I'm going to cover. And so thank you. End of course. Let's see. Recording.